Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the expressions for torque in terms of polar moment of inertia. Here, what is the torque? That is just a glimpse to recapitulate relation to the torque. Here, if we apply the bar is here considered as a circular cross section. When one end is fixed and if we give the twisting moment at the other end T, the effect of this twisting moment leads to develop the shear stresses and shear strains in the material of the beam, in the material of the bar. Here it is considered as a cantilever. So when the twisting moment is applied either in clockwise or counterclockwise direction, there will be the angle of twist. We can see in the layers the angle of twist. This torque causes to develop the shear stresses and shear strains inside the material. Now here, if we apply this torsion or torque to that is where there is a different slabs other than circular cross section, how that here also the shear stresses and the shear strains will be developed inside the material. Now this is the mode. This mode is known as the torsional mode or twisting mode. Twisting mode. Due to this twisting mode, at certain frequency, at certain natural frequency, the material behavior in a twisting mode in this manner, particular natural frequency. So the torque can be or the twisting. In this here also, what will be developed? The shear stresses and shear strains will be developed inside the material. Now coming to expression, this torque is denoted by capital T. The unit for torque is Newton meter, and the angle of twist is denoted by theta. The unit for this twisting, the angle of twist is radians. So we are going to express this torque in terms of polar moment of inertia. What is the polar moment of inertia? That is denoted by J. Torque, that is the J is polar moment of inertia. Polar moment of inertia. Now, polar moment of inertia of a plane area is defined as the moment of inertia of the area about an axis perpendicular to the plane of the figure and passing through the center of gravity of the area. The moment of inertia of the area about an axis, the moment of is perpendicular, an axis perpendicular to the plane of the figure, and passing through the CZ, center of gravity of the area. It is denoted by the letter capital J. So the torque in terms of polar moment of inertia is obtained from equation if consider the dt is the twisting moment on element dt on a circular ring, as we have studied in the previous session. The dt equal to small tau by capital R times 2 pi r cube dr. So tau by r, 2 pi r into r square dr. Now here, that is tau by r square and 2 pi r dr. If we send this 2 pi r dr is nothing but dA. Now this term is transformed to tau by capital R into r square. 2 pi r dr means dA, r square dA. This r square dA, now we are integrating this word elemental torque on the ring. That is small, that is tau by capital R square dA. So it is varying from 0 to capital R radius on the circumference. So 0 to R, the total torque equal to 0 to R dt. That means 0 to R, tau by capital R square dA. That is tau by R, that is integral 0 to r square dA. Now 0 to r and r square dA is known as the moment of inertia. The moment of inertia of a circle about an axis is r square, that is perpendicular to the plane of the circle and passing through the center of gravity, that CG, centroid of the circle. That's why this r square dA is known as polar moment of inertia, that is J. That is J equal to pi d power 4 by 32. How it comes here? According to perpendicular axis theorem, that is IZZ equal to IXX plus IYY. Now, what is IXX for a circle? If we consider it, it is x-axis and here it is y-axis. Now, what is the diameter here? The diameter is d. About x-axis, that is pi d power 4 by 30, pi d power 4 by 64, and about y-axis, that is also pi d power 4 by 64. Now, what is the IZZ? This IZZ is perpendicular to the axis, to the plane area in this direction, perpendicular to the circle. That is the polar moment of inertia that comes as pi d power 4 by 32. So, this is the polar moment of inertia, pi d power 4 by 32. Now, we know the equation that is T equal to tau by R times J. That is where J is here, as we have studied here. This is T equal to 0 to R tau by R times 0 to R square dA. This is tau by R. This R square dA is known as J. From this equation, it becomes a T by J equal to tau by R. Now, we are already derived here in previous session that a tau by R equal to C theta by L. Now, the equation, that is a pure bending, that means pure shear stress formula or pure torque formula, torsion formula is that T by J equal to tau by R equal to C theta by L. Now here what we have derived that T by J equal to tau by R equal to C theta by L. This is the pure torsion formula, as we have studied a pure bending formula. What is the theory of pure bending? That is M by I equal to sigma by Y equal to E by R. This is a pure bending. Similarly, in the same manner, in the pure torsion formula, this is T by J equal to tau by R equal to C theta by L. Now here, the similarities means here, in the case of pure bending, where E is the modulus of elasticity, whereas this equation, pure torsion equation related to shear stress, the modulus of rigidity is C, and radius of curvature R, radius of curvature here. In the case of pure bending, there is the bending stress, whereas in the case of torsion formula, there is the shear stress. Here, bending movement, here the torque, twisting movement. Here, in the case of bending, this is the second moment of area or area moment of inertia. This is the polar moment of inertia. So, the similarities, that form pure bending is applied for bending stress. The torsion formula comes when the twisting moment acts on the body or on the component. Now here, what is the T for torque? Unit for torque is, as we have studied, is Newton meter, where J is unit for J, that is the polar moment of inertia, that is millimeter per 4. If it is Newton millimeter per 4. There's tau is the shear stress, the maximum shear stress occurred on the surface of the section, that is Newton per square millimeter, and R is the radius of where here R is not radius of curvature, here R is the radius of the shaft, the maximum radius of the shaft, it is in millimeters. Whereas C, what is the C here? Modulus of rigidity, it is in terms of Newton per square millimeter. Theta is the angle of twist, it is in terms of radians. and where L is the length of the beam or length of the component or length of the structure, that is in millimeters. Now this is the formula T by J equal to where C for modulus of rigidity, theta angle of twist in radians, not radiation, radians, where length of L is capital L is length of the shaft. And what is the significance of this equation? The equation, pure torsion equation. The pure torsion equation T by J equal to tau by R equal to C theta by L. This equation is so important in order to find out the unknowns. Whatever input parameter based on the data, we have to use the relations T by J equal to tau by R or tau by R equal to C theta by L, and combinations of T by J equal to C theta by L. So these are the various combinations we have to use based on the given the data. So in order to find out the torsion, when the shear stress acts, when the torque acts on the body, immediately the material component, the material property of the material is modulus of rigidity comes into the picture. And where L is the length of the shaft, where L is the length of the shaft, J is the polar moment of inertia. So when the twisting moment acts, there is resistance to the twisting moment, that is known as here polar moment of inertia. Whereas in the case of bending stress, resistance to bending moment, that is not area moment of inertia, that is the area moment of inertia. Now here the polar modulus is very important parameter in order to find out the strength of the strength of a material or strength of the section here. So what is the polar moment of inertia? The polar moment of inertia is defined as the ratio of polar modulus is defined as the ratio of polar moment of inertia to the radius of the shaft, the maximum radius of the shaft. That is denoted by as torsional polar modulus, that is section modulus, polar modulus or torsion section modulus. It is denoted by Zp. So it is mathematically Zp equal to J by R. So what is the unit for this J by R? The polar section modulus unit is millimeter, cubic millimeter. Now for solid circular shaft, what is torsional section modulus? Substitute in the place of J and R related to the solid circular cross section, that is pi d power 4 by 32 by R d by 2. Then it becomes pi by 16 d cube Zp. Zp equal to pi by 16 d cube. This is for solid circular shaft. Whereas coming to for a hollow shaft, what is J value? Polar moment, that is polar. Here the J is that pi by 32 times outer radius d power 4 minus di power 4, and Zp equal to J by R. What is this R is? R is, what is D? Is this di by 2 or outer do by 2? So we are considering R is for the maximum radius, that is called this outer radius, that is do by 2. In the place of J, substitute as pi by 32 times do power 4 minus di power 4, and R is do by 2. After getting substitution, after substituting the values of J and R, then the transformed the section Zp equal to pi by 16 d naught times d naught power 4 minus di power 4. So these are the formulae highly important in order to calculate wherever the torsional section modulus are to be calculated. So, but these formulae are derived only for circular cross section and circular hollow circular cross sections. Now here the strength of the material, strength of your shaft and torsional rigidity are very important parameters for designing the shafts under the which are subjected to shear twisting moments. Now what is the strength of your shaft? The strength of a shaft means the maximum torque or the maximum power the shaft can transmit. So maximum torque or maximum power the shaft can transmit, that the maximum torque is known as the strength of a shaft. So here the capital T, that is the torque, is very important. The torque is more, that means it's the strength. Maximum power, the power P equal to T times omega. The power can transmit because the omega angular velocity, the torque is very important. How much torque the shaft is being transmitted at particular speeds. Now here torsional rigidity or torsional stiffness of the shaft. This torsional rigidity is mathematical here, that is a Cj. Cj is known as the product of modulus of rigidity times the polar moment of inertia of the shaft is known as the torsional rigidity. Okay, here, whereas in the case of bending stresses, we have studied as a flexural rigidity. So here it is, that is, their formula is m equal to E at E times I, where E is the modulus of velocity, I is the moment of inertia. Here it is Cj is the modulus of rigidity and J for polar moment of inertia. Now here the torsional rigidity is the Cj is known as the torsional rigidity C times, where C is the modulus of rigidity. Now we know the relation that T by J equal to C theta by L. Then what will happen here? The make combination T times L equal to C times J theta. And from here T L by theta equal to Cj. The Cj is known as torsional rigidity. The torsional rigidity Cj equal to torsional rigidity Cj equal to T times L by theta, where torque T is the torque and L is the length of the shaft and theta is the angle of twist in radians. So torsional rigidity comes when then torsional rigidity equal to torque when L becomes 1 meter and theta becomes 1 radian, then the torsional rigidity equal to torque. So this torsional rigidity equal to TL by theta. The torsional rigidity, there are two formulae here. One is a torsional rigidity C times J, another one is TL times TL by theta. So these are the two formulae derived here to understand the strength of a shaft and also torsional rigidity. Okay, now how to apply this formula while solving the problems. Now determine the diameter of a solid steel shaft which will transmit 90 kilowatts power and 160 revolutions per minute at 160 rpm revolutions per minute. Also determine the length of the shaft if the twist must not exceed 1 degree over the entire length. The maximum shear stress is limited to 60 Newton per square millimeter, that is the tau. Take the value of modulus of rigidity is 8 into 10 power 4 Newton per square millimeter. So these are the given data. First, power, that is the power trans 90 kilowatts. 1 kilowatt equal to 1000 watts. So that is 90,000 watts. The second is that at what revolutions per minute the speed, that is n equal to 160 rpm, and also the length of the shaft. We need determination of diameter d. Here it is, diameter is capital D, and L is the length of the shaft. These are the two objectives are to be found. Determine the length of the shaft and the angle of twist is not exceed, that is theta equal to 1 degree. 1 degree equal to, then it becomes theta 1 into pi by 180, that is pi by 180 radians. 1 into pi by 180, that is pi by 180 radians in terms of radians. Then the tau equal to the shear stress equal to 60 Newton per square millimeter. That is the shear stress. The next is the modulus of, the value of modulus of rigidity C is 8 into 10 power 4 Newton per square millimeters. So how to find out diameter of the shaft and the length of the shaft? The diameter of the shaft, here first we have to calculate the maximum torque that comes from power P equal to 2 pi nt by 60. The relation between power and the torque and speed is that P equal to 2 pi nt by 60, where P is 90 into 10 cube, 2 pi n, where n is 160, capital T by 60, where T is the torque. From this, the torque is calculated. The torque comes under here. The torque is here, if it is in watts, 2 pi nt torque. The Newton meter, convert into Newton millimeters in order to maintain the dimensional homogeneity. So here 5371.48 Newton meters. So 1 meter equal to 1000 millimeters. So they multiplied with 1000 at 5371.48 times 10 cube Newton millimeter. Now we know the relation between the torque, shear stress and diameter of the shaft. That is, it is a solid circular shaft. It's not a hollow. Yes, solid steel shaft. How can we know it is a cross section is? Because the objective is the diameter of the solid steel shaft. That's why we got to know is the solid circular shaft. So this is the formula that it indicates or gives the relation between torque, shear stress and diameter. Now T equal to pi by 16 times tau d cube. Now in this here, we know the unknown is the diameter, which is to be found, diameter of the shaft, the torque value and the tau value if you substitute here, that is T equal to 5371.48 times 10 cube equal to pi by 16 times tau. Tau equal to 16 d cube. Now we have to calculate the d value. That d value is obtained as 76.8 millimeters. The d equal to 76.8 millimeters. That is the diameter of the capital D equal to, that is the diameter of the solid shaft. Now there is another objective, we have to find out what is the length. How to find out the length of the shaft? Is there any relationship? Yes, we have the equation of the pure torsion formula. That is, what is the formula? Let us discuss here in this slide. For reaching the objective, the second objective is that we have to find out the length of the shaft. We know the pure torsion formula, that is T by J equal to C theta by L equal to tau by R. Now here, torque we know. Yes, from these two relations, we know the torque, we know shear stress, modulus of rigidity value, theta we know. J comes, what is it? J is pi d power 4 by 32. And L we have to find out. Okay. And here also there is another relation R. R is the relation of the shaft. Here also radius also we can find out. So if we use any two equations, there is equation 1 equal to equation 2 or equation 1 and equation 3. By using, we can calculate another method. Now here we see the tau by R equal to C theta by L. What is the tau here? 60. What is the R? R equal to diameter, we got it is 76.8. R equal to 76.8 by 2. And C theta, what is the C value? Modulus of rigidity. What is the modulus of rigidity? 8 times 10 power 4 Newton per square millimeter. That is 8 10 10 power 4. Theta, pi by 180. L, unknown. Now we got it L value. The L value is here. Length of the shaft is 893.6 millimeters. There is another method. This is one of the method. It is method 1. We can also calculate by using another method. Method 2. What is that method 2? The method 2 is that we know that T by J equal to C theta by L equal to tau by R. But we have to use this C theta by L because L is unknown to be found. Now T by J and C theta by L. What is the torque here? The torque value is calculated as 5371.48 5371.48 into 10 cube by J, that is solid circular, pi d power 4 by 32. What is the diameter here? That is 76.8 power 4. What is the C value? Modulus of rigidity 8 into 10 power 4. Theta pi by 180 and L. So from this also we can calculate L value. This is another method. It is not necessary tau by R equal to C theta by L. It is also T by J equal to C theta by L. But by using this L value, what is the L value? The L value will be obtained as similar. Should be obtained, then only it is valid. 893.6 millimeters. So we have studied two methods in this for calculating the length of the shaft. So there is only one way to calculate the diameter here. The twisting moment T equal to pi by 16 times tau d cube, or tau times pi by 16 d cube for that d. This is only one way. There is another way, no. So this is the calculations. Now coming to the next problem. Here in this problem again we have to find out the diameter of the shaft, and here the same model we are going to, for practicing the problem, determine the diameter of the solid shaft, which will transmitting the power of 300 kilowatts, convert into watts, that is 300 times cubic 10, that is 10 cube watts, at the speed of 250 rpm, at the speed of 250 revolutions per minute. So here one of the doubt here, 2 pi n, yes, we use the speed. Next, the maximum shear stress should not exceed, is the shear stress value tau, that is 30 Newton per square millimeter, and the twist should not be exceed not more than the 1 degree, that is called 1 degree equal to pi by 180 radians. In a shaft, length given, that is the L value is 2 meters. Here length was mentioned here, 2 meters, convert into millimeters, that is 2000 millimeters. Take modulus of rigidity, that is the C value. Take modulus of rigidity 1 into 10 power 5 Newton per square millimeters. Now what is the objective? Only one objective, that is the diameter of the shaft. What is the diameter of the shaft? Now here, how to start? The beginning here, we have to find out the diameter of the shaft. First, we know the relations. Please write down the relations between power, torque and speed. That is power P equal to 2 pi nt by 60. And after getting the torque and shear stress and diameter relation, torque T equal to tau times pi by 16 d cube. Is this solid shaft or hollow shaft? Yes, it is a solid shaft. So we have to use the formula in relation to solid cross section. Now by using these two formulae we can find out the diameter, which is unknown. But here unknown is the tau. The tau will come, the torque will come from this equation 1, formula 1. So from this formula 1, torque T is the unknown, power P we know, N we know, known. So power substitute here. Yes, power P, where is the power P? That is 300 times watts. 1000, 10,000 watts, 300,000. 2 pi n, where is n? 250 revolutions per minute. Capital T by 60. From this T comes the T equal to tau times pi by 16 d cube. Tau times pi by 16 d cube. What is the T? Calculating here T. Then after calculating that value here, substitute. Then tau, what is the tau? Shear stress 13 newtons per square millimeter. Please convert from this torque in terms of Newton millimeter. The value comes here, it is Newton meters. So that value should be multiplied again with 1000. Okay, 1 meter equal to 1000 millimeters. Pi by 16 times d cube. From that d will come. Let us see. Yes, begin. 2 pi nt by 16. Substitute known values. P 300,000, 300 into 10 cube, 2 pi n, 250 revolutions per minute, capital T by 60. And the T values obtained as 11459.110 cube Newton millimeters. We know what we need. Objective 1 is that diameter of the shaft. We know the shear stress. Tau equal to 13 newtons per square millimeters. Then T equal to pi by 16 times tau d cube. Now here T, substitute the value of the T here. This is the T. Pi by 16 tau, that's 30 d cube. From that D is 124.5 millimeters. That is the diameter of the shaft. Okay, here there are two. One more thing. Diameter of the shaft when maximum shear stress. Here we have to find out the diameter of the solid shaft. Okay, and also here the maximum shear stress should not be exceed, and also twist. We need two diameters. One is diameter of the shaft when power transmits the maximum shear stress, and also the twist. Now the diameter of the shaft we are going to calculate another manner based on the data, that is T by J equal to C theta by L. What the T here? Torque. What is J? Polar moment of inertia, pi by 32 times d power 4. So T value diameter power 4. C modulus of rigidity. The modulus of rigidity is 1 into 10 power 5. Yeah, Newton per square millimeters. Theta value convert into pi by 180. That becomes here pi by L. Length of the shaft is 2000 millimeters. From that, the value of D is obtained as 107.5 millimeters. So, from 1 and 2 equations, from one diameter value is 124.5, another diameter is 107.5. Which value we have to consider as the diameter of the shaft? So, for designing purpose, we have to consider the maximum diameter of both the two values is to be considered as the diameter of the solid circular shaft. So the diameter of the shaft, here it is, that is maximum of both values, that is 124.5, for in round figure, that is rounding, that is 125 millimeters. Alright. Now, if a diameter is taken as the smaller of the two values, say 107.5 millimeters, from that equation, what is the torque? The torque from that equation, for the same torque, the shear stress becomes, what is the shear stress value? That is 46.978 Newton per square millimeter. So the given torque value is how much? 30 millimeters. So if we are validating why we should consider the maximum value. Okay, if we take this diameter, suppose we consider 107.5 millimeters diameter value. From that diameter, you calculate the shear stress, how much shear stress is being developed. Definitely the shear stress will be developed is maximum value. But the given value is 30 Newton per square millimeters. So, in order to achieve that value, that shear stress, but the maximum here shear stress is being developed by taking the smaller value. So, if we consider the larger value for that same twisting moment, the capital T equal to pi by 16 times tau d cube. Alright. In that, take D maximum, larger value for the same torque, that is 11459100. That is pi by 16 times tau d cube. What is the D value here? The D value we consider it as 124.5. Now the shear stress will be, if you calculate this value, definitely that value will reach the given value, that is 13 Newton per square millimeter. So that's why the diameter of the shaft is considered is the larger of the two values to be considered, that is 124.5 millimeters. Okay. So in this session we have covered what is a polar section modulus, and we have expressed the torque in terms of the polar moment of inertia value, that is the J, that we have derived from that. That's pure torsion formula, that T by J equal to tau by R equal to C theta by L or G theta by L. So we learned how to apply those formulae while solving the problems. And also one more thing is how to design the diameter of the shaft, of the solid circular shaft. So for the given data, that's what we have learned in this session. And very important model is the final problem we covered here, the diameter. Consider the diameter at shear stress should not be exceed at the same time 1 degrees, that angle of twist not to exceed 1 degree, that is or pi by 180 radians for the same torque and for the same length of the shaft. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.